All right, we're recording. Screen is shared. I think we're ready to go. One thing worth mentioning here at the start of lecture is our next lecture is an exam. Normally we'd have a meeting for Monday, but that's when exam 2 is scheduled. So we won't meet on Monday. I won't be recording a lecture, but during that time, you'll be taking exam 2. I sent out a Piazza post about that, and there's a page of notes on our Moodle page. So be sure to have a look at that. There's already materials posted to help make sure you're ready for the exam. Any questions about that before we pick up where we left off? All right, we fell behind a little bit on Monday, so I'll try and catch us up. We got a good bit to cover. The exam, by the way, just covers the material through lecture 18. So that's a little bit of what we'll talk about today, and then I'll let you know when we switch over on that. We were covering this at the end of lecture, sort of C's plan for giving back information about an error. And it's this thing that looks like a global variable called errno. Lots of the documentation for standard C library calls have values you can look for along with a definition of what they are. So if you wanted to print out a diagnostic message or maybe know the right thing to do in response to an error, you could look for particular values based on the documentation. Like if you open a file and it fails, the value of errno, the numeric value of it will tell you something about why it failed. But if you just want to print out an error message, perr is a standard library function that already knows lots of standard errors. So when an error happens, it's common to, instead of checking the value yourself, to use perr to print out a human readable error message. It takes a string parameter, and that usually specifies something about what you were trying to do. I guess an example makes this easier to make sense of. If you try to open a file and you can't open it, and that could be for a bunch of different reasons, perr knows how to look at the value of errno and print out a message that says what went wrong. But you can include the name of the file you were trying to open, and that's what you could pass in as your part of this string. So you pass in a string of your choosing, and typically, like if you were trying to open a file, that would be the name of the file. In other situations, you might have to choose a string that makes sense. perr will print out the string that you give along with a standard error message for that, like file doesn't exist or disk is full or something like that. I mentioned already on homework number, on project 5, you get to use this to help you print out meaningful error messages. And this is the kind of thing that you might do if you tried to open a file and you would still check the return value of fopen to tell that something went wrong. But if you know that fopen failed, and that's what this if does, you could use perr to print out the error message. And here you can see I'm passing in the name of the file I just tried to open. And at least on the common platform, you'll get an error message like this one. The string you passed in, along with an error message generated by perr. And for different values of errno, it'll print out different messages. Questions before we move on to one more topic in lecture 18? One more topic in lecture 18, and that is a thing that we've been using sparsely all semester, the math part of the C standard library. You already know that if you want to use math functions, there's a header file you need to include, math.h. But that just lets you see declarations of math functions. They're in a different part of the library. So, and you already know this, I'm just reminding you, if you want to use the math functions, you also need to link with the math library. And that's what I'm doing down here. This -lm says link with the math library. If I don't do that, I'll get link time errors for functions like cosine or square root or something like that. When you include the header file, you get a bunch of stuff, or at least it declares a bunch of stuff. Some preprocessor constants, like a constant for the base of the natural logarithm, the value pi that we've probably used a couple of times, and the value of the square root of 2, that shows up a lot. And you already saw that some of these, like m_pi, is not really part of the standard library. So if you, although it's commonly defined in that header file, if you want to use it, at least on our compiler, you need to use the -d_GNU_source option. You'll need to do that in the next project, and you already did that in an exercise, and it's described in the project, so you don't have to remember it from this lecture. You also get a bunch of, so if I had to classify functions, that's what I've tried to do here. You get a bunch of trigonometric functions like sine, cosine, and tangent, and the inverse of those functions. You even get a 2-parameter tangent or arctangent function, which is kind of handy because it works for any quadrant, any y and x value in any quadrant, and it gives you back the angle between -pi and +top pi. All of these functions are defined for double, and that's what I'm showing kind of at the top. So they expect a double parameter or double parameters in case of the last one, and they return the value as a double. Now, what if we had a float or a long double that we wanted to compute one of these with? In Java, we'd probably just overload a method for this. But in C, we don't have overloading. We can't have 2 different functions with the same name. So they did what is commonly done in C. And you've seen a lot of examples of this. They gave the function a slightly different name to reflect its parameters. So for every one of these functions, they work on double, but there's also a version with an F at the end that works on floats. So sine, this first one, expects a double parameter and returns double. Sine F, just no underscore or anything, just sine F, takes a float parameter, and sine L takes a long double parameter. So there are, for each of the functions that I'm showing you here, there are typically 3 functions in the standard library that do that, just for different types of parameters. There are functions for exponentiation and logs. And I've tried to list all of these together so you can do exponentiation or log in the 3 bases that we normally use, the natural logarithm base, base 2, or base 10. And then there's some general, there's a square root function I listed down at the bottom, or the more general function for raising any number to any power you want, this pal function. I've seen a lot of you use that on various assignments, so you're probably, I mean, that's probably something that you saw in Java. And you may notice that in Java, their math class borrows a lot of the conventions from the C standard library. So a lot of the functions you're seeing here would show up, I think, as static functions in the math class if you were working with Java. And there are functions for doing rounding behavior or things that are kind of like rounding. There's a round function that works with doubles. There's an absolute value function that works for this FABS is for floating point absolute value. So it still works on doubles. It returns the result as a double. I probably should have been saying that for round because it makes more sense. So round rounds to an integer, but it returns the result of as a double rather than an int because int might not have enough range to cover all possible double values. So it does round it to an int. It just gives you back the result in a type that has enough range to store any value that you've rounded. So there's one for computing the absolute value, for floor and ceiling, and for doing a floating point mod. If you're coming from Java, the percent operator works for floating point mod, but not in C. Percent only does mod for integer types in C. If you wanted to do a mod with floating point types, you could call this function to do that. In practice, you don't need to do that often, but it is here if you need that. And that gets us caught up with where we should have been at the end of lecture on Monday. Thinking ahead to the exam next Monday, or on the, I think it's the 5th on Monday, that's where we'll stop in the material. So if you look at the study guide, it should include topics for everything we've covered up to what we just finished with. Any questions before we move on to what we're supposed to do today? Good, because I already closed those slides. I could go back. It would just take a moment. All right. So we've got a little bit of standard library. So for what would normally be the start of a day's lecture, we've got a little bit of standard library left over. And then we're going to go back and talk about program organization a little bit more, because we now know enough to do some things or worry about things that we probably didn't worry about before or couldn't have worried about before. First, 3 topics in the standard library: environment variables, variable number of parameters, and a mechanism that's kind of like the exception mechanism in Java. First, environment variables. If you've done any work in Shell, or if you're a Windows user, maybe if you've written any batch files in Windows, you're familiar with the idea of an environment variable. It's a variable that is available from the command interpreter that keeps values for you. And these are used for a lot of configuration things in your shell, like you've got a home variable on a Linux, on a Unix machine that points to your home directory. And in shell, the way you get to its value is you just put a $sign and then the name of the variable. So if you just get shell to print out what's in the variable home, you can do that by just saying echo, that just prints out anything on the command line argument. And then the $home set as to the shell, I want to know what's in the environment variable named home. You've got other things like environment variables that say what your path is, that say what your shell prompt is, that say what editor you prefer to use. So these are used for a lot of configuration things. And they're so common in the shell that you might think they're just a shell thing. But this is really something that's implemented in any running program that's written in C. All programs automatically have a set of environment variables that they keep up with. And there are standard library functions for looking at and changing the environment variables. And that's what I'm going to show you next. So if you're writing a C program and you want to look at an environment variable, and when I say that, I mean you want to know the value of an environment variable. There's a getEnv function that returns a string that takes as a parameter the name of any environment variable you want, and then it returns a string that's the value of that. When you get that string back, you're getting a pointer to statically allocated storage. So you're not supposed to free it. It's not malloc memory that's given to you. It's memory that's part of the environment, and you're just getting a chance to see one of the strings. So the string you get back here, you don't want to free that. You don't need to, but you can use it like any other string. Here I'm just printing it out. This lets you look at an environment variable, and this is one mechanism for changing environment variables. There's a 3-parameter function, setEnv. It expects name of the environment variable you want to change, new value you want it to have, so any string you want it to be, and then you can even decide how you want to handle default behavior here. If you put true as the last parameter, it will overwrite any previous value this environment variable has. If you put false there, then it'll only set that variable if it didn't previously have a value. So if it was already set, it'll just leave it the way it was. Environment variables are part of any process, and when your program starts up, if you looked around, you would see a bunch of environment variables are already set. They were set by the shell when it started up your program. So environment variables normally get, at least some of them, normally get copied into new programs as they're started. But this is just something that exists within a currently running program. So if you change a bunch of environment variables in your program and then your program exits, the shell will still have the old values for all of those. When you do a setEnv, you're just setting the environment variable within your currently running program. That's not going to change it for the shell once your program exits. So this is really, environment variables are really just a list of name value pairs stored within the standard library. They're stored within your program. The shell is smart enough to push those into new programs when it starts them running, but there's nothing automatic that copies them from one program to another. Questions about environment variables? So just a little mechanism in the standard library that you've probably used. You just maybe didn't know that it was coming from the standard library. Another trick that we've seen, but until today, we didn't know how to do it, is writing functions that take a variable number of parameters. We've seen a little bit of the syntax for this. So you've seen for printf, if you look at its prototype, it's defined like, well, for printf, you've got to give me a format string. But after that, there could be any number of arguments that come after it. And that's indicated, same as in Java, by ... So this is called a function that takes a variable number of arguments. In C, the rules for variable number of arguments are a little stricter than they are in Java. And well, like a lot of things, they're a little bit harder to use in C than they are in Java. In C, you've got to have at least one named argument, kind of like printf does. It's got a format string that's going to be there. And then after that, there could be any number of arguments. So you can't have a function that just takes ... It has to take one or more named arguments first. And then any arguments that get passed in after that we'll call unnamed arguments. And if you put this ... here, you're telling the compiler this function can take any number of arguments after this first one, any number of arguments of any type. When you call a function with a bunch of arguments after the named argument, when you call it and you pass in a bunch of things here, those get pushed onto the stack just like any other parameters to a function. And to look at those arguments, you have to go look at what's on the stack. And we could probably write our own code to do that. We could find out where things are on the stack and look around. The problem is the format of arguments on the stack is platform and compiler dependent. So if we wrote our own code to do that, it might work on one system, but then when we move that code to another machine, it might not work anymore because maybe that machine uses a different way of storing the parameters on the stack. Fortunately, the C standard library helps us out with this. There's a header stdarg.h, standard arg, that is made for helping to parse variable number of arguments. When you include this, you get 4 macros that are defined that are made for letting you extract command line arguments in a portable way. I'll tell you what these do real fast. It's what's listed on the slide here. And then we'll talk about how we would actually use them. And we'll look at, I think, 3 examples that show how these can be used. The first is a type. It's defined with help from the preprocessor, but the type is VA list. And that is for declaring state for keeping up with the command line arguments. What I mean by that is when you're extracting arguments from the stack, you're going to be saying things like, give me the next argument, give me the one after that, give me the one after that. So it has to kind of keep up with where it is in extracting those arguments. This is the state it needs to do that. So if you want to extract arguments from that ... parameter or from any number of arguments on the stack, you're going to need a variable of this type, VA list. Then you're going to need to call that first macro VA start. That says to start processing variable arguments. It's got 2 parameters, the VA list you just made and an argument that says where to start. We'll see an example of that in a moment. And then you're ready to start extracting arguments. Whenever you call that next macro, VA arg, you're saying, give me the next argument that was passed in. So if your function got called with 10 arguments in that ... slot, then you can call this 10 times, once to get each argument. When you call this, it expects 2 parameters, the state, that's this VA list variable you made, and the type of the argument, because if the caller could pass in arguments of any type, you've got to say something about the type you expect as the next argument. And then last, you're going to call VA end when you're done. That puts everything back the way it was. You should call that once when you're done processing variable arguments. Questions before I try to move on? I said this mechanism is a little uglier than it was in Java, and here's one of the reasons why. C doesn't have a mechanism for telling you how many arguments were passed in. Java, when you use variable arguments, you get an array of references to the arguments, and you can use standard array syntax for seeing how many they were and then for figuring out what their types are. But in C, you've got to do that yourself. Sorry, Java provides a good mechanism for that. C, you kind of have to do some of that yourself. There are two standard ways of keeping up with how many arguments were passed in. You could do it like printf does. If you think about it, printf can tell how many arguments to look for because it's right there in the format string. If you try to print something and you've got 2% Ds in the format string, that says you're going to have two integer arguments that were passed in. So you could indicate the number of, this would be a question of how you design your function. You could indicate the number of arguments by using one or more of the named arguments to give a hint. Or for different applications, maybe you could have some kind of an end marker so that you say, well, I'm going to pass a bunch of arguments and you know you've hit the last one when you hit something that looks like this. We've got examples of both of these, so let's take a look at them. The first one uses this first scheme, kind of like printf does. It uses the named argument to say how many arguments come after. It's kind of a silly function, but I called it add integers, and it'll add up as many integers as you pass it. So you could give it 10 integers, you could give it 50 integers, one after another as parameters. So here's how you might call it down here. We're saying add up 17, 42, 98, 3, and 27. I skipped over the 5 because that's what I'm using to say how many arguments follow. I'm going to use the first parameter as a way of telling the function, I'm about to give you 5 numbers, and I want you to add them all up. That's what goes in. If you look at how this function is called, that 5 is going to get passed in as the value of n. That's our named parameter. And the rest of these are going to get passed in this variable arguments slot. So I'm using the named argument to say how many arguments come after it. That's just a design decision for this. And then within the function, let's go through this quickly because it's the first time we've seen the var arguments mechanism. I told you about it 2 slides ago, but this is the first code we've looked at. So he said you got to make a variable of type VA list. That's what I do here. That's for storing state as we're extracting the arguments. I don't know what's in there. I mean, we could go look at it, but the point is I don't have to know what's in there. As long as I make a variable of that type, the macros I'm about to use will be able to use it to keep up with where I am in the arguments. And then you call VA start, at least before you start processing arguments. You call VA start. You say, here's where to keep your state. Here's where to keep up with where you are in processing the arguments. And here's where to start from. Normally, you'll pass in the name of your last named argument. I've only got one here. So this is like saying, start right after the n. All of the parameters to a function, all the arguments are passed in one after another on the stack. So this is saying where to start in memory. And then once I've done that, I go through n iterations because that's how many arguments I'm expecting. And I extract each argument. This is that third macro, varg. You give it the state and then the type of the argument. You need the type so that, among other things, it knows how much memory to get off of the stack. An int is going to take 4 bytes on the stack, at least on the common platform. A double would take 8 bytes. This tells varg how much memory to get off the stack and how far to move ahead for the next argument. So varg with a parameter of int goes and gets the next int off the stack. I do that not just once, but for however many arguments you said you were going to give me. I add them all up, and then at the end I return the total. But before I do, I call va_end to clean up things. So here in this design, this function, I'm expecting the caller to play nice. They got to tell me how many arguments follow, And I can't keep them from lying to me. So if they do something stupid, like they say, I'm going to give you 29 arguments, but then they only pass in 5 of them, they're going to trick this function into looking way past these arguments on the stack, potentially doing something bad, certainly getting some garbage arguments in doing that. So this mechanism, just like scanf, depends on the caller giving us a named parameter that makes sense, a named parameter that matches what they're actually passing in. Questions about this? You get to do this on your next exercise. You get to write your own tiny little pretend version of printf. Questions? All right, I said another way you could handle the number of arguments is you could have an end marker. That wouldn't always make sense, but here it would. Here I'm pretending I'm going to give a function a bunch of strings, and I just want it to print them all out one per line. So I want to be able to call it like this. Well, each of these strings is going to evaluate to a char pointer. So this function really takes a whole bunch of char pointers. All char pointers, at least all legal strings, are going to be non-null char pointers. So I could use a null as an end marker. No legitimate string would have null as its pointer. So I just use that as an end marker. Backing up, I couldn't really have done that. Sorry, couldn't really have done that here because maybe 0 is on your list. But here, null, well, no string would be null. So I can just use that as a way of marking the end. This function, I still have to have a named parameter. I called it first. But then after that, you can pass in as many strings as you want. I get ready to parse the var args. I set up my state to parse everything after first, but I better print the first string before I print any of the others. And then for the rest of them, I just keep calling var arg to extract the next char pointer. And then I print it out until I get a char pointer that's null. And then I know that, well, at least if the caller is playing nice, I know that I've hit the end of the list of the strings they wanted to give me. So I can quit processing arguments. I call va end and then I return. Questions? I got one more example, and that is, and this one of these, this is probably the most useful one. Let's say you wanted to compute the maximum of a bunch of values. You just want to know which one's biggest. We've seen how to do that with a macro, but that only takes 2 parameters. And we already talked about how if you nest the calls to that macro, it can give you it can blow up into an awful lot of code. This lets you write a function where you can just ask it for the max of as many values as you want. You can call it like this. I wrote it for floating point values, so it expects a bunch of doubles. You have to help it out by telling in the first parameter how many values you're going to pass in. So it doesn't use any kind of an end marker. You have to say, I'm going to give you 6 values. Here they are. Tell me which one's largest. Here, for the maximum, well, that only makes sense if you pass in at least 1 value. You can't compute the maximum of no values. So I did that with the type of the function. I've got a ... but only after the first double. So you have to give me at least 1 double. If you want, you can give me more than that. Within the function, I get ready to process var args. I take the first value you gave me, the one you had to give me, and that's my tentative largest until I find a bigger one. And then I go through, you said you were going to give me n values. So I go through the rest of them, extracting each double. So again, va arg to get the next parameter off the stack. But I expect it to be of type double. So every time I call this, you can think of it as moving 8 bytes ahead on the stack, the size of a double. And then if that's a new largest, then that's my current winner. Once I'm done, I clean up and then return the largest. 3 examples of var args, and like I said, you get to do maybe a more interesting example on an exercise this weekend. Questions? All right. Our last standard library topic And it's about what C would call non-local jumps. If you were coming from Java, you would probably think of this as exceptions. This is a C mechanism that's kind of like exceptions in Java. Uh, in fact, depending upon your JVM, this may be how exceptions are implemented when you call an exception in Java. What's it take to do what an exception does? Well, you've got to be able, I've got a picture that tries to show this. So what an exception does is you might have a function. In Java, we'd call it a method. You might have a function that calls another function that calls another function. And then if an error happens in that function, I want to be able to bail out of not just the function where the error happened, but potentially a bunch of functions I called along the way until I get to some error handling code, some code that knows how to handle that particular error. That's what a non-local jump does in C. Same idea. It lets you exit out of not just one function, but a whole stack of functions that have called each other until you get to code that, that you marked as error handling code. This is not nearly as pretty as it is in Java. I think when you look at a language like Java, it's a good bit newer, and this kind of feature became so useful that they built it right into the language. In C, when you use non-local jumps, you're going to be working a lot closer to how this is actually implemented, even if it's used from a language like Java. So to do this, we have to be able to mark a place that we want to jump to. That's kind of like a try block in Java. We need to be able to say, if anything goes wrong, you need to jump back to here. And part of doing that is declaring a variable of type jump buff. Sorry, I may have skipped the header for this. Yeah, there it is. Sorry, it's at the top of the slide. SetJump.h defines a type jump buff. And that is, it's usually called an environment. And it's like a picture of where you are on the stack. Let me back up so I can point to this little picture. Essentially, you want to be able to say, kind of like a try block in Java, if anything goes wrong, jump back to here. And to do that in Java or C, you have to remember, all right, here's where I jump back to if something goes wrong. This is a variable type that can remember that. So a jump buff is like a picture of where you were in the code and what's on the stack. So this can hold a picture of where you are in the stack. The way you take a picture of where you are on the stack is with this call, setJump. As a parameter, it takes the environment that we were just talking about. So this env backing up is a variable of jump buff type. So you can declare as many of these as you want. And then when you want to do something that's kind of like a try block, you can call setJump, and that remembers where you were in the code and where you were on the stack. It also returns a value. And that's probably the trickiest part of explaining this. Because when you call it, the first time you call it, it returns 0. So usually, when you call it, you're going to call it in code that looks like this. You're going to say, take a picture of where I am on the stack, and then see if it returns 0 or not. And the reason for that, and this we'll see this in some other examples, the reason for that is when you jump back to this, so you can see this as taking a picture of where you are in the code right now, in case anything goes wrong in later code. If anything goes wrong, it's going to jump back to exactly the same call. In fact, it's going to look like you just finished a call to jump buff, except instead of returning 0, it's going to return a different value. So the return value from jump buff is your way of telling, was I just taking a picture of where I am on the stack, or did something go wrong and I jumped back to this line of code? So a return of 0 means you were just taking a picture of where you are on the stack. So here's, again, this little bit of code is kind of like a try. The stuff inside these curly brackets is kind of like the try block. Do this code, but if anything goes wrong, jump back to here. So we've seen, how do we store an environment? How do we mark a spot on the stack to jump back to? And that's what set jump does. What do we do when something goes wrong? How do we jump back to there? That's what this next function does, long jump, LONGJMP. That lets you stop what you're doing, exit out of the current function, and all of the functions that called it, all the way back to the set jump that you used to initialize this environment. I've got my next slide has a picture that shows this a little bit better. So here, this is kind of like a throw in Java. When something goes wrong, you call long jump, and that jumps back to, again, whatever set jump initialized this environment. Just like a try catch in Java, this is for jumping up the stack. So exiting the current subroutine, the current function, the function that called it, the function that called it, all the way back to the line in the function where you called set jump on this environment. This second, so the first parameter is the environment you want to jump back to. The second parameter is the value you want it to return. I said, well, normally set jump returns 0 when you're just taking a picture of the environment, but if you jump back to it, it can return a non-zero value. Here's where you pick what you want it to return. So you're saying jump back to that call to set jump, but this time return a 1 so that it can tell something went wrong. All right, so we've learned 3 things about this, the jump buff, set jump, and long jump. And here's how you would normally use them. So pretend these little blue blocks are parts of functions, or they're 3 different functions. In your code that has the error handling, so this is kind of like the try catch code, you'll declare an environment, you'll take a picture of where you are on the stack, and as long as nothing went wrong, as long as that returns 0, you're going to execute a bunch of code. That code could include calling a function. That function could call other functions. They could call other functions. But if an error happens and you want to jump back to error handling code in your caller, or the function that called your caller, or the function that called that one, you can do a long jump back to that environment. So this is the same environment variable that I declared here, and get it to return a different value. And that'll quit exiting this function. It'll bail out of the function that called you all the way back to this function, and it'll look like you're right back on this line of code, except instead of getting a 0 return, you'll get a 1 return. So you won't do the body of this if. In fact, you will typically write this code like this. If set jump returned to 0, then I was just initializing it. So I'll go try to do whatever code I would normally try to do. This is kind of like the body of the try. Inside that, if a long jump executes, it'll jump back to this set jump, except now it'll return, in this case, I said to return 1, so it'll return 1. So instead of taking the then part of this if, I'll take the else. I'll do, so typically you'd put error handling code there. If you got inside this else, it's because you jumped back to this call to set jump and it returned something other than 0. So this is kind of like a catch, or sorry, this is kind of like a try. This is kind of like a throw in Java, and this is kind of like a catch. If this returns a 1, do this piece of code. In Java, you discriminate different types of errors by the type of exception that gets thrown. In C, you just do that with an integer value. So long jump of 1, you could use that to mean one kind of error. If you want a different error handling code, you could do a long jump and pass in some other number here. And then in the caller, you could dispatch to the right error handling code based on the numeric value that got passed back. Normally, you would use the preprocessor to define constants for that kind of thing. So this is kind of pseudocode that shows how you might use it. This code's a little, in fact, this is spread across 2 slides and it shows a more realistic application. Let's say we want to read a bunch of users, or sorry, we want to read a bunch of values from the user and add them all up and print out their sum. So I've got a top function that calls this middle function. So here's the call, but you can see it's kind of in a try block. It's got a set jump, and if anything goes wrong, it's going to jump back to the set jump, and then we'll print out an error message. In the middle function, well, its job is to read a bunch of values and add them up, and then it just prints out the sum of those values. What's read values look like? Well, that's on the next slide. It reads a bunch of values from the user, adds them all up, and then returns the sum. But since it's the function that's actually doing the reading, it can tell if there was an error in the input. And if it's reading a bunch of values, it's going to read until it gets, it's going to read values for as long as it can. And it's expecting only integer values, at least based on how it's written. As long as it gets an integer, it adds it in and tries to read another one. It should be able to do this until it hits EOF, until there are no more inputs, because that's what scanf does. It returns EOF when there's no more input. But what if there's garbage? What if the user just types in something that isn't even an integer? Well, this is going to fail, but it's not going to return EOF. It's just going to return 0. That's what we detect right here. If the user ever gives us garbage, we just discard all of the input and long jump back to the error handling code. That was on the previous slide, but if you let me back up, that's going to jump all the way back up to here. And then we're going to print out invalid input. A good thing about that is when I long jump, I skip all the way over this inner function, this middle function. Moving ahead, or sorry, this function calls this one, and then it calls this one here, read values. But if there's bad input, this long jump bails out of read values. It bails out of this middle function, which means it doesn't print this sum message, which is probably good if we had, if the input was garbage. So we don't finish running this function, and we jump all the way back to the top function and then just print out an error message. So this, just like try-catch in other languages, Java has try-catch, but other languages have that same kind of mechanism. Just like try-catch, this lets you consolidate your error handling code. You can put that in higher level functions, and you can worry about just putting error detection in your lower level functions. One more thing to mention about this example is, notice that the function, let's go to the bottom function here, the one that's reading values. How does it get the environment? We pass it in as a parameter. In Java, this kind of thing's done automatically, but you can think of the parameter to this function as saying, if anything goes wrong, here's where you need to jump to. In fact, the middle function, backing up, it does the same thing. We give it an environment, and then it passes that to the read values function. So we have to do it ourselves, but we can pass environments around as parameters, and you can think of that as saying to a function, here's what to do if something goes wrong. So here's a bigger example. I've got one more example. We'll try to go through it quickly. And that is, what if you had some cleanup to do? What if you had a function that mallocked some space? And if an error happens, you want to make sure you free that space. Otherwise, it's going to look like leaked memory. In Java, we would handle this with a finally block. So we really just need to figure out how to simulate a finally block using this jump mechanism. Well, since we get to control what environments we're using, like we just said, the way we've written this code, we're passing those around as parameters. we get to control the environments we're using, and we get to control when errors are thrown, when we do a jump, a long jump, and where we put the catching code for that, where we put the set jump. We can add in our own code that works just like a finally block. And that's what this middle function does. I've changed, so it's the same kind of example as before. I got a function that reads a bunch of values, except instead of just adding them all up, it stores them in a list. And then the caller goes in and prints out that list. So it's not quite the same thing we were doing before. It also, instead of reading them from the user, let's pretend it gets them from a file. So before the caller calls this function, it opens that file. On the way out, it frees the memory for the list, figuring it allocated it, so it better free it. And it closes that file, figuring, thinking, I opened the file, someone better close it. And it looks like it needs to be me. But what if an error happens in read values? Well, we just said this could exit out of this function without running any of the rest of this code. But if an error happens, we really need to make sure these two functions get called. We need to close the file and free the memory for that list, even if we don't do this, even if we don't print out all the values that just got read. And if we had an error, maybe it doesn't make sense to print the values if some of them were garbage, but we do need to clean up after this function. So these two lines are kind of like what we put in a finally block in Java. Those are two things that need to get done, even if a long jump jumps past this function. How can we do that? Well, since we're passing the environments around, we can just make a new environment that lets us stop off at this function, even if an error happens in the function that we call. So same middle function, I've just changed it. We still open a file, we still malloc some space for a list, but when we call read values, instead of telling it to jump all the way back to code in our parent, we make our own environment. That's what I'm pointing to here. We declare our own environment and we snapshot where we are on the stack here. And then when we call this read values function, we say, jump back to here if an error happens. Well, if it does a long jump and that jumps us back to this set jump, we will, instead of returning immediately to our caller, if we get a return value other than 0, that'll take us down to this else. That'll give us a chance to close our file and free the memory for our list. And then we can keep jumping from there. Then, oops, sorry, I pushed the wrong button. We can close the file, free our list, and then jump to whatever the parent wanted us to do when an error happened. So this, by passing read values a different environment, we can get the chance to stop off here if an error happens. And that covers most of what I think we need to cover for the standard library. This last topic is probably a little bit tricky, but if you use it in an example or two, it doesn't take that much to get used to, especially if you're used to the exception mechanism from Java. Questions before we change topics a little bit? All right, I said we would talk a little bit more about designing a project that spans more than one component. And that's what we're going to talk about next. We already did this on day 6. We talked a little bit about, well, if you've got a program and you want to spread it across multiple files, how can you do that? And so we've learned the mechanisms for that, things like using function prototypes and using header versus implementation files and separating the compile and link phases. But there's still more that we can think about in how we should design a piece of software, how we should design a component. And that's what we're going to do here for a little bit. We're going to look at some alternatives for how you could build a component. So we mean a When we say component, remember, we mean an implementation file, a .c file, and a header file that advertises its interface that says, here are all the things you can use in this implementation file. We're going to look at a few different ways we could design something like that. And to try to keep the example simple, they're all going to do the same thing. They're just going to do it differently. They're going to implement a set of values. And initially, that's going to be a set of integer values. So they're all going to provide functions for working with a set. And I've listed them here. They're all going to have a make set call, and that lets you initialize the set representation. They'll have a function for adding a value to the set. They'll have a function for asking if the set contains a particular value. So that just returns yes or no. And then a function for cleaning up the set when you're done called destroy set. And all of these examples are posted with today's material. Most of the code we looked at in class are posted underneath the lecture slides for that. Here, because we'll look at, I think, 4 different ways of doing that, it adds up to quite a few examples, but they're all just small changes from the previous example. So first, I guess some terminology. Some of this is obvious for how we could do this. We're going to have a set component that implements these 4 functions, and it's going to come in 2 pieces. Like any component, it's got a .c file that has all the implementation, and it's got a header file that just describes what the set is like. As a rule, you want to make your header file as small as you can. We've probably talked about this a couple of times. You want to put as little as you can in the header file, because whenever you change that header file, anyone who used your component has to recompile. Normally, if we have code that uses other code, we might call it client code. And that's what I'm pretending I've got over here. So you've got a piece of code that uses your component. Well, that means it probably includes your header. Well, that means when the compiler compiles the client code, it also sees the header code because it got included. And any changes in the header code would affect the client. It would mean you need to recompile it. So anything you put here is more expensive to change. Any code, any line of code you put in the header, if you change that line of code, everyone who used that component has to recompile. Whereas if you could put it here, if you could leave it out of the header and put it in the implementation file, then you only have to relink. You don't have to recompile. So that's why I say changes to the header generally are more expensive. Over on the left, imagine if we had to make some important change to standard.io.h. Now, every piece of code that includes that would at some point have to recompile. So changes to your header, it's worth it to remember, those are much more expensive. So that being said, let's try our first implementation of a set. So up at the top, I've summarized the header. I just put prototypes in the header. I didn't even put any type definitions because I'm trying to keep the header as small as possible. So when you call make set, it's going to initialize the set, but it's not even going to tell you what it did. You can insert a value. If you give me the value, you can ask if a value is contained there. You can tell me when you're done with the set, but you don't see anything about how the set is implemented. I hid all of that in the implementation file. And if you look down at we're pretending this is the .c file. Well, as we've said before, it includes its own header as the first line of code. That's a good practice. But it's going to, internally, it's going to implement the set as a linked list. 1 value per node. So there's the value, there's the pointer to the next node, there's the head of the list. And I don't have the whole implementation here, but it's posted with the examples if you want to look at it. If you call make set, I just set the head pointer to null. If you insert a value, I go, well, it's supposed to be a set, so I don't want duplicate values in the set. So I first go look and see if it's already there or not. And then I didn't include this code, or I didn't show it on the slide because I ran out of room. But then I allocate a node for it and store it in the list. If you ask me about if the set contains a value, we just walk down the linked list and look for that value. And then when you ask me to destroy the set, we just free the space for all the nodes. So a pretty straightforward implementation of a set based on a linked list. This is kind of a summary of what the implementation could look like. This is client code that uses it. So it's just showing how you would use it if it was implemented like this. So first you'd call make set, and then at the end you would destroy the set when you're done. In the meantime, you can insert as many values as you want, and then you can ask if the set contains a particular value or not. So again, this is just showing how you could use it. The thing we just built, your textbook would call this an abstract object. For reasons that we already talked about. You get to use this implementation of set without really knowing how it works. And in a way, that's a good thing. It means that the implementer could change how it works, and your code shouldn't have to change at all. But there's some disadvantages to the way we've implemented this. And we kind of talked about this earlier in the semester. The problem with the way we built this set, backing up, the way we built this is there's only one set. When you call make set, you don't say which set you want to build because there's only one. When you call insert value, well, you don't tell what set to insert it in because there's only one. So this has limited use if it can only represent one set at a time. We could do better. We could make it so that this same code, or almost the same code, can store as many sets as you want to work with. But it's going to require some changes. In particular, we're going to have to give away, or we're going to have to define some kind of type that represents a set. If we want to let client code make 10 different sets, we need to give them some kind of object that represents a set. So that's what I did here. I defined a struct called set, and you can make as many of those as you want. It's really just a wrapper around my linked list. So when you make a set, you get a new head pointer for that set. And if you made 10 of these, each of them would contain its own head pointer. Well, because node is the type for the head pointer, to be able to talk about the node type, the compiler needs to know what that is. So it means I had to put node in the header. If you back up a couple of slides, it used to be in the implementation file. It was hidden from client code. But here, to let client code use a set, I also had to expose node. I had to show that in the header file. And this is what I said I don't want to do. At least a couple of slides ago, we said, as much as you can, you'd like to leave things out of the header file. But now my header file has to contain not just these functions, but these two types, which means if I changed them, if I said I'm not going to do a linked list anymore, I want to represent a set as a bit vector maybe, then that's going to force client code to recompile. We'll fix that, but first let's talk through how this works. So now make set, since you could have as many sets as you want, you have to give me a pointer to a set, the set you want me to initialize. In fact, for all of the other functions, when you want to put a value in a set, you have to tell me what set it goes in. When you want to ask if a set contains a value, you have to tell me the set. When you want to destroy a set, you have to tell me the set to destroy. So notice here, we're always passing the set by address. The caller has to make an object, they have to make a struct of this type, and they just show it to make set or insert value or contains value whenever they want to use it. I had room for even less of the implementation, but it's all posted if you want to look at it. So in my implementation, well, I still include my header first. And then for initializing a set, I'm counting on you to have already made the set. I just need to go in and fill in its head pointer with a null. So again, this initializes what's in the set structure, but I'm counting on the caller making a set and just passing in the pointer, like the client code is doing here. So this is the same kind of client code. This is just using this new implementation of a set. They have to make an instance. So if they want a particular set or if they want a bunch of them, they have to declare variables of that type. But this S would be uninitialized. It's just a stack variable. Who knows what its fields contain? Before they can use it, they've got to call the make set function, backing up the one we were just looking at here. To initialize that, then they can insert values in that set as many times as they want. Notice I've got ampersands before all of these S's because S is an instance of set, but all these functions want a pointer to a set. So I get the address of that set. And then I add a bunch of values. I can ask if that set contains a bunch of values, and then I can clean up when I'm done, or I can ask the component to clean up when I'm done with the set. So this is nice. This example code just makes one set, but we could make as many as we wanted. So now we've got a set that's maybe a lot more useful than what we started with. I've seen this mistake a lot. In fact, we talked about this already in the semester. This is just a chance to remind you of that. Since all of these functions expect a pointer to a set, it's common, or it's a common student mistake to say, oh, I need to give make set a pointer to a set. So let me make a pointer to a set and I'll just pass that in. And this will compile, but it's a bad idea because if you think about what the set is going to do with this pointer, you give it a pointer, and backing up a few slides, it's going to use that pointer to try to access the head field. Well, moving ahead, if you made your pointer like this, it doesn't point to anything. There is no set object that it points to. So if you pass so it's really just an uninitialized pointer. If you pass that uninitialized pointer to make set, when it tries to use it to get to fields in the set object, who knows what memory it's going to be accessing. Probably this is going to crash your program right away. The plan for this function is that you're going to use it like this. You're going to give it the address of a set that you already made, and it'll go in and fill in all of its fields. So here, sorry, again, I'm just showing this because it's a common mistake. Questions before we move on? I hope some people are there. Everybody's been quiet today. But Zoom says we've got 51 people. So hopefully we've got an audience. Questions? All right, moving on. So I already complained about this. And it was, well, to do what we just did, to make it so that client code can have as many sets as we want, we had to expose a lot of how the set is implemented. We just saw that. We had to put the set object in the header, and we had to put the node object or the node struct in the header. And this is bad. In general, we want to hide as much as we can in an implementation file and expose as little as we can in the header. And I've listed some reasons why here, and they vary in importance. Maybe your implementation is really secret and you don't want other users, other programmers to know about it. That's probably not that realistic, but maybe that's important to you. Making the header larger is computationally more expensive. Every time someone uses your header, the compiler has to go get the code for that header. So a giant header file is more expensive to compile against. That's less important. But that thing we already said, everything you put in a header is more expensive to change. If you change, like backing up here, and I said this before, if we wanted to change how node was represented, or we wanted to not even use a linked list, every piece of code that used the set would have to get recompiled. And imagine a lot of people are using this code. That could be expensive. And that's probably the main reason to try to do what's called insulating code from changes to our implementation. The more stuff we can put in the implementation file rather than the header, the more we've done to insulate client code from changes to our component. There's a trick that's going to let us do this that we haven't seen until today, and it's called an incomplete type. C will let you declare some types without defining them. Just like with declare versus define. When you declare a thing, the compiler knows that it has a name and it knows something about what it is, but it doesn't have its whole definition. We've seen this with functions. A prototype is a declaration. It tells the compiler about a function, but it doesn't know the body of the function. You haven't defined the function yet. You can do the same kind of thing with a struct. In fact, here's how you do it. If you say struct and then any struct name you want, but then instead of defining the struct, you just put a semicolon. The compiler will know that that's the name of a struct. It just doesn't know anything about what's in the struct. But that's still enough to let you do some things with the struct. You can even do this as part of a type def. So on the next line, I do a type def struct, and I pick a long name for a struct, but then I type def it to a shorter name. Incomplete types like this let you use the type, but only in certain ways. And those certain ways are called name-only use. You can't do everything with a struct if you don't know what's in it, but you can do some things with it. In particular, you can use pointers to it. List struct, knowing that it exists, is enough to let you take pointers to that type, but you can't declare variables of that type. You can't access its fields because you don't even know what the fields are. You can't, in general, if you only have an incomplete type declaration for a struct, you can use pointers to it, but you can't do anything that depends on the size of the struct. So you can't directly malloc space for it. You can't get to its fields. You can't declare variables of that type. But just being able to use pointers to it is enough to do a lot of things. And that's going to let us hide our implementation of set using this trick of an incomplete type. If you have an incomplete type, you can at least use pointers to that thing, to that type. And you'll sometimes hear these called opaque pointers. You can have a pointer to a thing without knowing anything other than the name of that thing, or at least the name of the type for that thing. Again, that's called an opaque pointer, and that's what we're doing down here at the bottom. This is what our header could look like if we try to use an incomplete type. So up here, I'm giving a short name for my set struct, but I'm not saying anything about what's in it. I'm saying to the compiler, oh, I want set to be a short name for the struct that I'm going to call set struct. But I don't even tell it what that struct is or what's in it. But this is enough for the compiler to know, okay, set is the name for some struct. I can't let you declare variables of that type, at least not yet, but you can use pointers to it, and that's what I did in all of these prototypes. So now make set gives you back a pointer to a set. You don't have to pass one in. It makes a set and gives you back a pointer to it, and all these other functions just expect a pointer to a set. But I didn't have to give away anything about what's in my set implementation, just that it's the name of a struct type. I'll define that in the implementation file. Oh, and I skipped this term here. So we would call this an abstract data type. You can make a set, you can make as many of them as you want, but you don't have to know anything about how the set is implemented, not even how it's stored. I hid all of that and removed it from the header file. Questions? All right, sorry, I'm not smart enough to look at the chat while I'm
Oh,
talking.
so I have a
Sorry, go
question.
ahead. Yeah.
Okay, so like if you wanted to implement the methods like you have here, that goes in like a separate file, right?
Yes, and I was just about to show that. So this is
Okay.
the header.
Yeah.
What did it take to implement this stuff? Well, at least here's enough of the implementation to give you the idea. It's posted on the site. This is just what I could fit on a slide. So the .c file would look something like this. I'm going to include my own header. And right here, I'm going to go ahead and say, oh, you know that set struct I talked about? Here's what it looks like. So the compiler would say, oh, now you can use more than name only use. You can allocate space for the struct. You can access its fields because you bothered to tell me the rest of its definition. But I didn't have to put this in the header. So client code can use that pointer without knowing anything about the kind of thing it points to, other than that it's a struct. So here I fill in the definition of a set struct. Here's where I say, oh yeah, it's got a head pointer and that uses node. But since I never talked about node in the header, I didn't have to define it in the header. So all this is now this is now hidden in the implementation file. Client code is insulated from changes to this. Now, if you call make set, well, you couldn't pass me a set because you couldn't have made one yourself, but I can malloc space for a set, initialize its fields and give you back a pointer to that. I have to be smart enough when you ask me to destroy a set. Well, since I allocated space for it, I better free that space when you destroy it. But so here the implementation knows what these types are, but client code doesn't have to. So client code can include the header. It can use set, but only in, like we said, name only use. But that's enough to get a pointer to a set that's made by this function, to call functions that are only expecting pointers to sets, and to call a function that knows how to clean up a set when it's done. All of that was said sort of in response to a question, but I kind of fast forwarded in the lecture. Did I answer the question, or were there any other questions while we're at a break? All right, we've got one more refinement we can make. We just made what I would call an abstract data type. In fact, I did call it that. You can make as many sets. Oh, sorry. We made an abstract data type. You can make as many sets as you want without knowing how a set is implemented, but they're always sets of integers. What if you wanted to make a set of strings or a set of doubles or something like that? You ought to be able to do that. At least we ought to be able to figure out how to do that without having to rewrite the same code over and over again. We've got a new name for that, and we'd call it a generic abstract data type, kind of like generics in Java. In Java, you might do this with a type parameter. You might declare a template for, sorry, I'm trying to remember the Java terminology for this. I think they're called generics in Java, and they're a way to define a class that has a type parameter. C doesn't have that. So we're going to have to do it ourselves, but this is a common way of taking an implementation and making it work for as many types as you want. We've only got a couple of minutes left, but I think we can get started on this. Actually, let me reconsider that, because if we get started right now, we won't be able to finish it up until after the exam. So I think instead of getting started with this, here's where we'll leave off. And we'll pick this up. It'll be a week from today, but we'll pick this up. And I think we've really just got one more refinement to this implementation, but we'll save that for then. I'll go ahead and stop recording, but if people have questions, I'll hang around for that and I'll catch up on the chat here. So.